Okay, so now let's talk about asymptotic AdS. Before I do that, just for completeness, let me go back and just say here, you can stop the video and look at it if you want. I won't pause for long. You can always pause it. Those are actually the transformations to go between the hyperbola coordinates and the embedding and the Poincaré AdS coordinates, which can sometimes be useful. You can see, for example, just covers half the hyperboloid. Okay, but on to asymptotic AdS. We've talked about AdS spacetime. We've seen it's got a conformal boundary. An asymptotic AdS space is basically a space that shares the asymptotics of AdS but isn't AdS. So it has a conformal boundary, as for AdS, but it isn't an AdS space. And it will typically, in our context, it'll obey some dynamical Einstein equations. So there may be matter, a negative cosmological constant, gauge fields, who knows what, and gravity. Or we could just have gravity on its own with a negative cosmological constant. In fact, that's what we'll look at. But in general, it will be a solution of some sort of Einstein plus negative cosmological constant lambda plus matter. And here we'll focus just on either there being no matter or the matter not being excited. Okay, so it turns out that in what we call top-down embeddings or top-down constructions rather of AdS-CFT, you can have very complicated supergravity theories, lots of dimensions. There can be extra dimensions, there can be a sort of AdS part, all sorts of matter fields, form fields, and so on, scalars, dilitons. However, if the vacuum supports an AdS cross something space, you can always just focus in on the d plus one dimensional part, the AdS space, and think of an effective Einstein plus cosmological constant that determines the dynamics in that space, and solutions of that, just gravity plus the cosmological constant, you can then always embed in this much more complicated construction. Okay, so we'll ignore all the other matter fields. You can put them in, everything becomes more complicated. There's lots of interesting physics. But just thinking about Einstein plus cosmological constant, these solutions can always be embedded in these more complicated constructions. Okay, so in particular, we'll just be interested in this theory. As I've defined my conventions, the Einstein tensor is minus lambda times the metric. And this lambda is given, it's negative, and it's given, it's dimensional dependent, but in particular, it's got 1 over the AdS length squared in it. And of course, as before, we had that our curvature Ricci tensor obeys this, but it now doesn't have to be AdS. It doesn't have to have, for example, vanishing Weyl curvature, which is what AdS space does. It can be more general. Okay, so we're interested in solutions to this dynamical gravity theory that have the right asymptotics. Let's have some examples, and nice examples to write down are some black holes. So let's look at global AdS Schwarzschild. Let me just write Schwarzschild here. Global AdS Schwarzschild looks very much like the global AdS metric we wrote down before. And if we wrote this would be the global AdS metric, but it's very neat. We just get an extra term like this, and this turns it into a black hole. F vanishes at the horizon, very analogous to normal Schwarzschild, where we just wouldn't have this term here. Okay, so it looks very similar, and in particular, if we take alpha is R0 squared over AdS length plus 1 R0 d minus 2, then we see that the horizon is at R equals R0. So it's a nicer parameterization. So F vanishes at R0. The horizon is a sphere. It's a sphere. So this is d minus 1 sphere. So it's a d minus 1 sphere of radius r0. And so it looks very similar to the normal black holes we know and love. Now, we can also we can consider solutions called planar AdS-Schwarzschild, which is a sort of deformation of the Poincaré chart. So remember, in the Poincaré chart, AdS looks like this. This is the Minkowski metric. And so it's very simple. Remember, it only covers half the hyperboloid. It only covers a wedge of the global structure of AdS. Now, if we replace in here a function f, this is a different function. I'm just calling it f again, but of course it's a different one. Like this. We're in d+1 dimensions, remember, for the full space-time. So these are both d+1 dimensional. So the boundary is d-dimensional. That's why I'm using that convention. With this function f here that looks like that, we then again get a black hole space-time. So this has a horizon now at z is z0, and in both these spaces, in this space as r goes to infinity, in this space as z goes to 0, we have our conformal boundary. And the conformal boundary in both, in this case, for example, this is again this defining function. When it goes to 0, z is constant, so that term drops. This is our nice regular metric, and it's absolutely clear when z is 0 here, well, f is just 1, so the boundary here is again just Minkowski. And a similar way of analyzing tells you, again, the boundary here is just time across the sphere, this Einstein static universe. So, so again, we see exactly the same. So yes, sorry, let me just go back. By the way, this Einstein static universe, yeah, no, that's fine. So we see exactly the same structure. They have the same asymptotic, same conformal boundary, but of course they're not AdS space. Now, something that's important here, something that's very important here is that the horizon is a sort of Euclidean geometry. Okay, it's just Euclidean flat space, and so it's infinite. And this is already telling us that the physics of black holes, therefore, in AdS, the physics of these global black holes, it looks more similar to Schwarzschild. They've got a spherical horizon, but you can have black holes in AdS with a planar horizon. This, by the way, it's rather subtle. Whilst global AdS and Poincaré AdS are just related as coordinate transformations, so one is a portion of the other, this spacetime is not the same as this spacetime. They are different spacetimes. So it is not the case that this is some coordinate transformation of this. Once you start deforming, they just are different spacetimes. This one has a spherical horizon. This one really does have an infinite horizon. So the physics of black holes and AdS can be very different. In particular, we can have an infinite horizon, which is rather strange, and really is at the origin of the gauge gravity correspondence, if you've heard about it, which is the idea that the physics of these black holes, because the horizon is infinite, you can sort of change the temperature of the horizon as a function of these coordinates. And because it's the infinite horizon, you can do it slowly in a sort of gradient expansion, and that's how you develop this gauge gravity duality. Anyway, I won't be talking about that. That's quite a bit more complicated. Let me return to some more. The Hawking temperature of this space is something you'll calculate in the problems, but if you calculate it, you should find it's related to Z0 in this way. And in particular, it's with respect to the killing vector d by dt. You have to pick a killing vector when you compute a temperature, and d by dt is the sensible one to do it with respect to, in the sense that it's the one that generates time translations, both in the interior and in the boundary. But in particular, taking this defining function, our boundary metric is just Minkowski with this time. So this, if you like, is the temperature that someone living near the boundary using these this measure of time would perceive the temperature to be. And in particular, we can see that as Z0 goes to 0, this space, if you like, here becomes essentially, at least if you're sitting at some position in the bulk and you take Z0 to 0, this becomes more and more like AdS, because this term, sorry, Z0 to infinity, I do apologize. If you take Z0 to infinity, you basically kill this term, and then you go back to f being 1, which is just Poincaré AdS. So provided you don't zoom along with the horizon as you do it, we recover AdS in Poincaré coordinates. And so we can think we could have wondered, what is this? I sort of drew this diagram earlier. Poincaré AdS again a bit looks like this. It's got a boundary, a conformal boundary, but it's like this slice of the space. It's got these null surfaces, which I talked about. What are they? Well, in fact, if you like, they're like a horizon that's gone to 0 temperature. So these are really like an extremal horizon, the 0 temperature horizon. And we should think of them really as just some Cauchy surfaces. And in AdS, you can extend past them. But if you put them at any finite temperature, these become the black holes of the horizon. Okay, so Poincaré AdS has Cauchy horizons, which you can think of as an extremal horizon with some particular extremal horizon geometry. Again, we could define, the black hole entropy, as usual, is the area over 4 times g Newton, but here it's infinite. So how do we think about the situation where we have an infinite horizon? Well, one can do it in various ways, but a convenient way to do it is to, we could think about compactifying, and we'll think about that shortly. This, rather than having as an infinite space, we can wrap these up on a torus, and then we could think about the horizon having a finite area. So for example, if we wrap up the XA to be a torus, so now the boundary geometry is minus dt squared plus sort of d of a torus, let's say d of a torus, of length size sort of volume L d minus 1, then this area now becomes perfectly finite. It's just L squared over Z0 squared times the volume of that torus, which is L to the d minus 1. And that would give you the finite area. And so now, and equivalently, one could talk about densities. If you wanted to take the infinite case, rather than wrap it up on a torus, instead of talking about entropy, you'd have to talk about entropy density on the boundary. Okay, a couple more comments that we can now understand by looking at these black holes. GTT is sort of very important. It determines redshift in the bulk, as usual for static solutions. And we can see that it goes to infinity near the boundary, and obviously to 0 at a horizon. And if we think about Poincaré AdS, Z goes to infinity is this sort of extremal horizon. It's this Cauchy surface. So GTT does go to 0 as Z goes to infinity. And so we think of physics near the boundary as sort of high energy physics, in the sense that if you're in the bulk and you look towards the boundary, you see stuff very blue shifted. On the other hand, if you're in the bulk somewhere and you look down into the infrared, it looks very low energy, and so we think of that as the infrared of the geometry. So there's this sort of terminology that we've got our boundary here, which is like the UV, and say in Poincaré AdS, you can think of the IR living far away from the boundary. And in the field theory in AdS-CFT, sort of physics that happens at high energy tends to happen near the boundary, and likewise at low energy down near the infrared. Okay. Note that you can't just sit at a constant z in these spaces. You can't sit at constant r or constant z without accelerating. They're not geodesics, and so things tend to fall down to the infrared. Okay, so if you look at geodesics, things fall away from the boundary to the infrared. The boundary, in a sense, the conformal boundary, in a sense, repels things. Stuff wants to, go away from it. If you look at a time like geodesic, it does something like this. It'll be repelled. Good. More generally, in AdS, let's look at this sort of global picture. We could take some initial data, initial Cauchy surface, with some data on it. We fix the boundary. We've got some fixed conformal boundary geometry. And then we can evolve the solution in the interior. And so, we've written down some static black hole solutions, but really we should think about gravity always dynamically. And the correct data to impose is a sort of Cauchy data initially, but also, as I mentioned before, you need some data on the boundary, and that, if you like, is fixing the conformal boundary geometry. As we'll discuss, you can vary the conformal boundary geometry. And in particular, if you've got other fields in the interior, it's the same thing. You'd have to define Cauchy data for them and also some boundary conditions here. Okay, so you can have very complicated, you could have just our static black hole sitting there in this space, but you could also have, for example, two black holes coming together, merging, giving off radiation, bounces around, all sorts of complicated stuff happens. Okay. Now, I want to just say something about a little bit more about the boundary, and in particular in AdS, in asymptotic AdS spaces, we have a boundary stress tensor. I'll just call it the stress tensor. We know in asymptotically flat spaces we can define a mass and a momentum of a spacetime there using sort of the ADM formulas, for example. But in AdS spaces, in fact, in general in GR, whenever you have got a boundary, there's a natural Brown-York stress tensor you can define on the boundary, on a real boundary. But it's also true at a conformal boundary, or maybe true at a conformal boundary. And in AdS conformal boundaries, it is true. And so we can define a stress tensor. And so, in fact, we define the mass of an AdS space. In fact, we do even better than defining a mass in a sense. We can define locally on this boundary, we can define a stress tensor. So we don't just get a mass, we actually get an energy density and stress. Pressure, for example, if it's simple, but more generally, energy density, energy flux, and stress, living as a function of where you look on the boundary. So it's actually a nice, there's lots more structure. And in order to extract that, we need something called the Fetherman-Graham expansion. In fact, they did it for hyperbolic spaces, but if you flip the sign to Lorentzian, you do it for AdS spaces. So they were geometers thinking about hyperbolic space. And the Fetherman-Graham expansion, we can understand it as physicists working this way. It's like choosing, we've got our defining function, we've got our defining function, which is basically the z here. And then in our regular metric, we take Gaussian normal coordinates to z equals 0, the boundary. So this is like Gaussian normal coordinates with this defining function. And then if we write things like that, Fetherman and Graham, using some analysis, showed that, so they showed it sort of formally mathematically, but it's very easy to see just doing an expansion of the Einstein equations. In fact, interestingly, it was seen in the context of de Sitter in cosmology by, who was it? the name escapes me now, but anyway, a famous cosmologist, even slightly before Fetherman and Graham did it. But the point is we can expand this metric h in the following way. Let me write it like this. In even powers of z for a while, up to a term here, which is z to the d. And if you are in even boundary dimensions, odd bulk dimensions, there's an extra term here in this power series expansion. So this is only for even d. You get this log term. So we can think of this as a Frobenius expansion or regular singular point expansion of the Einstein equations about z is 0. You basically get two sequences, one starting at z to the 0 and one starting at z to the d. So these here, this is the boundary metric. This is the conformal boundary metric. Because, of course, if we look at what the boundary of this regular metric is at z is 0, well, it's just given by this term here. So this is the conformal boundary metric, and we can think of these as tensors living on G bar, and in fact, they're equal to curvatures. They're constructed from local curvature terms of this boundary metric. So this, for example, will involve the Ricci tensor and Ricci scalar of this. This will involve squares of that and also derivatives of that, and so on. So these are dimension dependent and slightly complicated. I won't write them down, but in particular, these are all determined by this. And this is like the second solution in a Frobenius expansion. It's second. The equations, the Einstein equations, are second order, and so you get these two solutions: one starting at z to 0, one starting at z to the d. This is the second solution. And so all of these are determined by just this until you get to this order, and then both of these then determine everything forever after. This, by the way, this extra log term is one of these. It's determined by this. Okay. So this bit of data here, let's say this is the data. These things are the data, and this bit of data is the boundary metric. You're actually free to vary it. So we know what it is now for AdS. In global charts, it's the Einstein static universe. In the Poincaré chart, it's just Minkowski, which we can think of as part of the Einstein static universe. It's only defined again up to a Weyl scaling. You can show that the Einstein static universe is Weyl equivalent to being flat. However, this other bit of data essentially determines this stress tensor. So it's, if you like, this is the asymptotic value of the metric, and this is its controlling its fall off to that value. So it's a bit like the 1 over r fall off that controls mass in usual asymptotically flat setting. How do we construct this stress tensor? Well, it's a little bit subtle. It turns out that this stress tensor looks like this. It's constructed, the stress tensor is constructed from this term, this second bit of data here, but there potentially is some other contribution here that you have to subtract off first. So this is local curvatures of this boundary metric. And it's only here for even d. So for odd d, basically this thing up to some factor here is the boundary stress tensor, this term, and this isn't here. In even d, it's a bit more complicated. You've got this extra term, and then this, you have to subtract off something. But once you know this, you know what to subtract off to construct this. And then this boundary stress tensor is conserved. And this really is, if you look at the work of Brown and York, this is really the what we would call the renormalized Brown-York stress tensor. The naive Brown-York stress tensor is actually divergent in AdS, but if you sort of renormalize it appropriately, you get a finite answer. So in d equals 3, for example, we would just have that this is 3. Let me write this constant. You can see this constant here is this effective central charge. It would be equal to this times this. Okay, so very simple formula. In d equals 4, it's more complicated because you've got these extra, you would have 4c effective t mu nu minus a bunch of stuff, okay, which I'm not going to write down because it's quite complicated, but I will write it when I finish this part. I'll fill it in and flash it up so you can see. Note, if the boundary metric, and this is relevant for some of the calculations you do, is of the form as it is for AdS, of this, if we have it in this ultrastatic form, like this, then we can interpret the energy density of the space as the time-time component of the stress tensor, and therefore the total energy of the space is actually given by the integral of this energy density over, so this might be a function of the boundary generally, but it's the integral of this over the spatial section. And that gives you then the total energy of the space. This is the energy of the space. And that is, of course, conserved. Well, it's, yes, it's conserved provided the boundary metric is unchanged. Okay. If we change the boundary metric here in time, it turns out you can then send sort of energy into the space-time. And energy won't be conserved. Okay, so some of the calculations in the problem sheet ask you to look at this boundary stress tensor, to extract it, and then calculate the energy from it. Okay, and this is how one would go about doing it. Okay, so that's the end of this part. Next time, we'll look at some sort of black hole physics, and in particular use some Euclidean methods to calculate it.